Hello and welcome. Let's take a detailed journey through the concept of electrical resistance, breaking down every part of this image in a clear, step-by-step way. First, let's talk about what electrical resistance actually is. In simple terms, it is the opposition, or friction, that an electric current faces when it tries to flow through a material. A great way to picture this is to imagine you're walking down a hallway. If the hallway is empty, you can walk through it very easily. But, if the hallway is crowded with people, you will constantly bump into them, and it will be much harder and slower for you to get to the other end. In this analogy, you are like the electric current, and the people in the hallway are like the atoms inside a wire. Electrical resistance is caused by the flowing electrons of the current colliding with these atoms. The more collisions there are, the higher the resistance will be. The symbol we use for resistance is the capital letter R. So, how do we measure this opposition? The official unit for resistance is the ohm. Its symbol is the Greek letter omega, which looks like a small horseshoe. To understand what 1 ohm represents, think of it this way: if it takes 1 volt of electrical pressure to push a current of 1 ampere through a circuit, then the resistance of that circuit is exactly 1 ohm. This brings us to a very important rule in the world of electricity, known as Ohm's law. The formula is simple and powerful: V equals I times R. Let's break down what each letter means. V stands for voltage, which is measured in volts. You can think of voltage as the electrical push or pressure that gets the current moving, similar to the water pressure in a garden hose. I stands for current, which is measured in amperes, often called amps for short. Current is the actual flow of electrons, just like the amount of water flowing through the hose. And finally, R is the resistance we've been talking about, measured in ohms. It acts like a blockage or a narrow spot in the hose that restricts the flow. The simple circuit diagram you see in the image shows this in action. The battery provides the voltage, or the push, and the resistor, shown with that zigzag line, provides the resistance, or the opposition to that push. Now, let's get more specific. What exactly determines the resistance of an object, like a piece of wire? For this, we look at the resistance formula for wires, which is R equals ρ times L, divided by A. This might look a little complex, but it's very logical. First, we have the Greek letter rho, which stands for resistivity. This is a natural property of the material itself. For example, materials we call conductors, like copper, have very low resistivity, which means they let current pass through very easily. On the other hand, materials we call insulators, like rubber, have extremely high resistivity, making it nearly impossible for current to flow. Next in the formula is L, which stands for length, measured in meters. This part is simple: a longer wire will have more resistance. This makes sense if you think back to our hallway analogy. A longer hallway means a longer journey with more chances to bump into people. Then, we have A, which is the cross-sectional area, measured in square meters. This is simply the thickness of the wire. A thicker wire has a larger area, and therefore has less resistance. It's like the difference between a narrow, single-file lane and a wide, 4-lane highway. The highway allows for much more traffic to flow with ease. Finally, we have to consider temperature. For most common metals, as the temperature increases, their atoms begin to vibrate more and more. These jiggling atoms get in the way of the flowing electrons, causing even more collisions. The result is that for most metals, a higher temperature leads to a higher resistance. Looking at the diagram of the cylindrical wire, you can see these physical properties visualized. The current, I, flows through the wire, which has a specific length, L, and a cross-sectional area, A. You might also spot the handwritten note, P equals VIW. This is a bonus formula for electrical power, which is measured in watts. It tells you how much energy is being used, and it's closely related, because the energy that is lost due to resistance is often converted into heat. So, to summarize everything, electrical resistance is the opposition to current flow, and we measure it in ohms. Its behavior is described by the simple and elegant Ohm's law. And the specific resistance of a wire depends on 4 key factors: the material it's made of, how long it is, how thick it is, and its temperature. Understanding these core ideas is the key to understanding how electricity works in all the devices we use every day.